Welcome all of you to today's presentation on PicoScope electric vehicle testing. My name's John Parker, I'm Distribution Sales Manager for Pico here in the UK. And I'm joined today with Pete, from an associate of ours from Hevra, and we're going to be learning all about the company he's involved with later on, and also Ben, who's one of our automotive technicians specialising in EV testing here in the UK. So yeah, we're going to start to take you through the basics of working with PicoScope on electric vehicles. Okay, right, we've got quite a lot to get through, but I'm just going to start by taking you through our new electric vehicle kit and the information on this kit, and of course all of our kits available both on our automotive website, so that's www.picoauto.com, and also more recently our automotive app that you can download either on Google Play or on iOS devices. So that's where to find more detail. But I'm going to take you through the main parts of the kit that are specifically important for working on electric vehicles. And then we're really lucky today to have Ben and Pete, who are going to actually show you working live on vehicles. We're going to do some live testing, but also we're going to go through the theory involved with all of those tests. So here are our two kits, and EV kits, like all of our kits, are available either in a carry case or probably most useful for a workshop, actually available in foam trays, so you can make your own diagnostic workstation. So just running through the kind of main EV elements, accessories within the kit. So we've got our PicoScope 2-pole tester. So this is really part of our safety regime, and you're going to hear a lot about safety today, and we make no apologies for that. So everything that we do has to, of course, be running within the appropriate safety guidance within your own country. All of the guys working here in the UK are up to level 4 EV testing, and a 2-pole tester is absolutely essential to that, to make sure that the vehicle you're working on has no voltage in it. Alongside that, we also have our insulation tester, and so this is again about safety and working on high voltage, but also is a multimeter, can be used as a normal multimeter as well. So two really essential pieces of the kit that operate outside of PicoScope to make sure you are absolutely working safely on vehicle. Then we start to get into the accessories that we attach onto channels of PicoScope. First one being differential probe. So this is a 1400 volt, and again, with all of these items, you know, you absolutely run with the guided tests that are involved within the software. And then we've got free current clamps. So the reason that we have free current clamps in the kit, and they are exactly the same as the current clamps available in the normal PicoScope kits, just means that we can look at all 3-phase motors for all 3 phases if we need to. So that's why there's free in the kit, but they are exactly the same. So the beauty of buying a PicoScope EV kit actually is the fact that not only are you protecting your workshop for the future, i.e., you know, you're buying a kit that will be perfectly usable on the future electric vehicles, you can use it on your normal ICE, so your internal combustion engine vehicles, right away. Then we've got backpinning probes. Most of you, I'm sure, are familiar with backpinning probes, but we've got these 1000 volts, so they're safe to use working on electric vehicle environments. Of course, you know, back to safety, you're not going to be working on live current or live voltage, and as you'll see as the guys start to work on the cars, of course they're wearing gloves and the appropriate safety equipment for making any connections. Ben, were you going to talk a little bit about why we have these as a Cat 2 backpinning probe?
Yeah, thanks John. So the Cat ratings. Now, for those that don't know, especially in the UK, the regulations for any working on mains is separated out into different Cat ratings. So a bit of an overview of the image. So Cat 4, we're talking about anything coming from the grid into the main building itself. So this is Cat 4 related products. Cat 3 is at the distribution board, so we're talking about being on the fuse boards, etc. like that. Cat 2, actually at the plug sockets within the household, and then Cat 1 is basically you using the equipment. We've gone with Cat2 rated probes. The reason why we've gone for the ones that we have is basically because they give better access. There's not many Cat3 rated probes out there that will allow you to backpin. So why can we not use why can you use Cat2 with a Cat3 differential probe? Well, the reason is that actually if you attach a probe that's of a lower Cat rating, you automatically derate the whole thing. So in our guided tests, when we talk about using the diff probe, especially for the charging communication stuff, which technically is on the low voltage side, so you could argue, well, I could just use a ×1 test lead in that situation. Not really, because you're connected to the mains. So automatically, then you come underneath the Cat ratings. With our guided test, we stipulate that you use a mode 2 charger, which is the one that actually plugs into a wall socket. For that reason, we are in this Cat2 band. So actually, even though we've technically derated our differential probe to Cat2, it's still perfectly safe to use in that environment because we've got the protection all the way back down. All right, so I hope that helps to clear that up. Thanks, John.
Thanks, Ben. That's excellent. Okay, so then kind of moving on, we've got our resistance test lead. So you'll see, and we concentrate a little bit on this today, a lot of the issues that we're starting to see with electric vehicles is, of course, on the charging systems, and the resistance lead is a really important part of that. So we're looking at type 1 and type 2 proximity line resistance. So that's a really important new addition to the kit. And then perversely going back, we do use the coil-on plug probe. So for anybody who isn't aware, the coil-on plug probe was developed for looking at coil-on plug systems. So on the old internal combustion engine. But what we've found and learned is that this will view a signal on any actuator, and it's really, really useful again when we're looking at charging systems, so charging coming into the vehicle. So really, really useful test, and again something that we're going to look at live on vehicle a little later on. Okay, so that's the basics of the kit. Like I said, there's a lot more components within the kit. You get your standard test leads and a whole range of clips and adapters, but hopefully that gives you an understanding of the main specifically EV elements included within our electric vehicle kits. So something that we've all had to do, and we're all going to have to do when working on EV, is starting to learn a new language. And to help with this, we've put a really nice little animation together, which takes you through the main electrical components that drive our new electric vehicles.
A great deal will change in our low-carbon future, but essentially much will stay the same. We still need energy to propel our vehicles, yet we will also need to learn a whole new language. Instead of burning fuel to generate energy, we will now fuel our vehicles using electrical energy. And for this, we need the Electrical Vehicle Supply Equipment, or EVSE. Power is sent into the vehicle via the onboard charger, or OBC, which converts the alternating current, or AC power from the EVSE to direct current, or DC power, in order to charge the battery pack. The battery can also be charged directly with DC power using suitable chargers. Rather than a fuel tank, an electric vehicle has a battery pack, with a majority of battery electric vehicles using lithium-ion batteries. Lithium-ion batteries have the advantage of being able to store more energy compared with previous electric vehicle batteries. Batteries like to be kept at a constant temperature to maintain efficiency, so thermal management is important, with coolant conditioning and air ventilation used to maintain battery temperatures. To manage the power available from the battery, electric vehicles use an inverter and converter. Its job is to modify power coming from the batteries so it's compatible with a motor, whilst also ensuring the correct voltage goes back to the battery during regeneration. Battery electric vehicles use an electric motor, or sometimes multiple motors, to drive the wheels. These motors are generally a variation of an AC motor. Due to the buildup of heat during operation, electric motors are often cooled with a separate coolant circuit. Due to an electric motor's instant torque and high RPM abilities, most BEVs use a single-speed gearbox. Although the energy supply and transmission are very different on an electric vehicle to those of an internal combustion engine vehicle, some other parts of the drivetrain are more familiar and despite EVs never shifting gears, they can still have similar top speeds. Additionally, battery electric vehicles still have a 12-volt or 24-volt electrical system to run all of the vehicle's peripheral functions, including cabin fans, lights, steering and braking systems.
So hopefully that helped you start to form an understanding of the various components within the electric vehicles. And as we said there at the end, of course, everything has changed, but also there's a lot of components that are exactly the same on cars that you're familiar working on. Okay. So we're going to get now over to some live test demos. So I'm sure this will be more interesting for everyone. So we're going to start working on car, on vehicle. We're going to run through these 3 tests live today. So we've got a range of guided tests within the software. So this is from the PicoScope 7 software now. And those 3 tests, we have 2 are already guided tests in the electric vehicle section here within the software. And then there is a new one. We're going to be looking at 3-phase motors, and that will be included within the software by the end of the year. So we're going to start with safety. Of course, we absolutely have to, and we're going to look at a zero potential measurement. And we're going to use our 2-pole tester here to measure that. So very quickly, our first part here is to test the device to make sure that it's working correctly. So we're pressing the button with our 2 poles together. And then again, we're double verifying everything. We are reading the voltage across our battery, again, to make sure that that probe is working correctly before we do any testing anywhere else. And then we are going to go back to the test port of the vehicle and we're going to get our 0 voltage. So we are double checking that the 2-pole tester is working before we do anything, and then we're coming onto the vehicle to again check that everything is 0. And then again, we're going back to the battery to verify that it's still working. So it really is triple, quadruple checking everything we do before we work on the vehicle. So that's the theory. I'm going to pass you over to Ben, and he's going to show you now live under the bonnet on our test vehicle how we do a 0 voltage potential test.
Okay, thanks John. So we'll have a look at the 0 volt potential. Now within PicoScope 7, there is actually the electric vehicle section now. You do have the warning that you do actually have to accept this, just to make sure that you're aware of all the inherent dangers and risks that are involved with working on high voltage vehicles. As this is a safety test, obviously it's under safety, and we have 0 volt potential. Now you'll see here there's no settings file, so as John said earlier, this device is a standalone device. It's not physically connected to the PicoScope software or hardware in any way. Click Guidance Settings, and then we have a bit of an overview of basically what John went through just a second ago. So as you scroll through, you'll see that there is how to perform the test. There's also actually a video here as well. There's a supporting video. And a number of our EV guided tests, there actually are supporting videos for these. Do have a look. There's either myself or Steve here in the UK actually running through these tests that actually give you a visual idea of how we're going to do it. But obviously we're going to do this today as well. So we've already made the vehicle safe and actually powered it down and locked the vehicle out. Do always make sure you follow the vehicle manufacturer's instructions when it comes to safely powering these vehicles down. Yeah, all the information is with the vehicle manufacturer. So, safety first, as we said. So I'm going to take our gloves, make sure they're not leaking. Now, take our 2-pole tester. I'm just going to make life a little bit easier by snapping the probe in the back. And we're going to press the button, as John said earlier. There we go, we actually have an indicator light there as well. Touch the 2 poles together, and there we have an actual segment test as well. So it's showing you everything that's going on, making sure that all the parts of the screen are illuminating. This also does a continuity check on the leads to make sure that they can actually detect a voltage between the two. The cable itself does also have a wear indicator, so should there be any fraying or it gets caught, there will be a white part of the lead that gets exposed. In that event, then we will need to get the device back and we can get that repaired. So first off, we're happy that our leads are good, so we're going to go to our known voltage source. In this case, it's going to be our 12-volt battery. Try and get it in a position that you can still see what's going on. There we have, so we can still read 12 volts. We go now to our test point, which is then the actual DC cables coming into the inverter. Touch the probes across that, and there we have. We have nothing on the screen, indicating that there is an absence of voltage. We go back to our known voltage source to actually detect, see if we can still measure a voltage, which we can. We still have 12 volts. Now, one of the questions we sometimes get asked is, well, is the device actually capable of measuring the voltage at the battery? Well, we have a nice easy test here. We can actually use the insulation tester. So by inserting the probes, they're on 4 mils, so they go straight in. We can set our insulation tester to defaults to 500 volts. Now, if I press the test button, this will start to output 500 volts. And there we go. So our insulation tester is saying that we have 526 volts, and our 2-pole tester is saying 526 volts. And it's also measured there as DC. That just helps to make sure that the 2-pole tester is more than capable of detecting that higher voltage. It also means that in the event that you will actually, or hopefully never actually see that there is a live voltage when you've done a 0-volt potential, but it also gives you an indication as what the device will actually be outputting when if that was to happen. Okay, I hope that helps. Okay, so we're now going to take a look at the charging communication. This vehicle is actually a Type 2. There's obviously Type 1 and Type 2 amongst other types. Predominantly these tests are around the Type 1 and Type 2. So we're going to look at how the EVSE talks to or communicates with the vehicle and how the vehicle communicates back to the charger to actually indicate it's ready to accept a charge. Within PicoScope 7, again, there are the guided tests. We can see here that we have a bit of an overview of what they are. Now, because we are connected to the mains, we are going to require Cat-rated products. Now, this means that we're going to use the diff probe and any backpinning probes associated. So we mentioned earlier that the Cat-rated Cat2 backpinning probes are used. If there are other ways of getting into that circuit, then do that. But obviously, backpinning tends to be the easiest route. A bit of an idea of what the signal actually looks like. And what I'm going to do is I'll hand over to Pete just to talk through the animation.
Yeah, so this is just a reminder that, as Ben spoke about the Cat ratings earlier, what we have is, here we have just a normal 3-pin plug socket as we have in the UK, or a normal domestic socket that we'd have in other markets. It's then got a box in the middle of the lead that handles the communication, and it will turn the supply on, and then it's got the vehicle connector on the other end. Now that we can use with our Cat2 rated equipment in order to measure that signal. The other types of charging equipment that we saw, for example, a properly installed charging point or a public charger, would theoretically need a Cat3 rating, so they're not suitable for use with this.
Not with the backpinning probes
with the
anyway.
backpinning probes.
Yeah, absolutely. Yeah. So we continue with the animation. We obviously get some of the warnings that we typically see with all of our EV-related information, and obviously the statement there. Make sure the VM data has got all the information. If you follow the right wiring diagram, you may find that there's an easier access point to get to that control pilot signal. So here we have the Type 2 socket, and here we are indicating the CP line, and now that goes back to the onboard charger. And we swing round and actually show how we now connect to it. So here we have the differential probe, making sure that you're on the right settings, and connecting to that CP circuit. Connect the charger, and this is when the communication starts to take place. And what we'll do is we'll run through this live as well. So we'll get it up on the screen. We'll show actually what happens when you connect to a live vehicle and it starts to charge. And we can see that signal should change. So hopefully when we get the signal up, Pete's going to talk through the different states that we're expecting to see.
Yeah, and what's nice about this is because this is a standardised communication that all vehicle manufacturers and all charging point manufacturers use, although there are some very minor differences with different vehicles, it is a standard and it is going to be the same on any vehicle that's got a Type 1 or has got a Type 2 connector.
Right, let's flick back to the software. We're going to go to our guided test. Again, we need to accept the warning. This is a charger vehicle test, and we're going to look at the Type 2. So we're going to load the guide and settings in. So this will add a preset into PicoScope. So everything's set up for you. So you just need to follow the instructions. Again, there is another supporting video there and a bit of an idea about how to make the connection, how to perform the test. So I'm going to minimize the guided test. I'm actually going to start the software. Now it's already asking probe mismatch, another nice new feature of PicoScope 7. So with all the EV guided tests, they were made with a 4425A scope, which means that we have probe recognition, so BNC+. The differential probe is not a BNC+ device. However, because the way the software and the hardware interact, even if you haven't got a BNC+ device probe connected, it will still ask you to make sure what you've got connected. It will ask you to select it. And we're on the ×20 range. Right, I'll run round.
So Ben's going to go around to the charging socket and plug your vehicle in as if we're going to start charging. Okay, and straight away we can see things happening on the screen. So if you could pause the waveform somewhere around there, please, Ben. And then we'll talk about what's happening. So the first thing that happens, there's two very important things that happen with this communication. They're both safety related. And the first thing is that we don't want any live voltage on the charging cable until it's connected to a vehicle. And the second thing is we don't want to overload the supply. So the supply needs to say what current the vehicle is allowed to take, and then the vehicle will make sure it doesn't draw more than that. And that's with the supply, the cable, and the vehicle in mind. So the first thing we have is that the supply equipment will output 12 volts and it will put that into the vehicle. And also the moment you connect the vehicle with that charging cable, what we refer to as vehicle ground, the vehicle body, our 12 volt battery negative, becomes linked to the mains ground. So the earth pin on the charging cable connects to the body of the vehicle, so the vehicle is now earthed. The charging cable then puts 12 volts down that control pilot communication line, and what you'll see when you look on here is we don't actually see 12 volts. Now the reason for that is as soon as we connect to the car will pull that down to 9 volts. So that being pulled down to 9 volts, because that this voltage is being measured both by the vehicle and by the supply equipment then knows that it's got a vehicle on the end. So the next thing that happens is that the supply equipment will then alternate that voltage from 12 volts to -12 volts. So it'll we'll start getting a square waveform 1,000 times a second, and if we zoom in, we can see we've got this square waveform which the supply equipment is putting out from 12 volts to -12. But as we said, the vehicle is actually pulling that down to about 9 volts, so we don't actually see the 12 volts. But when you look on the negative part of the waveform, you can see the negative part does come down to approximately 12 volts. And the reason for that is we have a diode, an electrical one-way valve inside the vehicle, so that it affects this part of the waveform and it doesn't affect this part of the waveform. Now the reason that we have that is an additional safety feature, because in theory this charging socket could have been put in a puddle, it could have damage to the wire or something like that, that could just happen to pull this voltage down just the right amount for it to think there's a vehicle on the end. And because the supply equipment is looking for a change in the top half of the waveform and not in the negative part of the waveform, that means it's only going to turn on that supply if it's got a semiconductor device on the end, i.e. a vehicle.
Absolutely.
Now, if we can just zoom in and look at that square wave again, please, Ben. the reason we have the square wave is partly so that we can have both the positive and the negative for that safety feature we've just talked about, but also the pulse width of this square wave actually tells the vehicle what current it's allowed to pull from the mains, and that means that we're not going to overload whatever we're connected to. So we can measure that using the features built into Pico 7.
Absolutely. So all I've done there is I've just drawn out 2 time rulers, and we've gone into the measurement function, and this is a positive duty cycle PWM signal. So by putting the measurement rulers in place, we can measure at that point in time, and we have a duty cycle of 20%. Now that 20% will actually give you a rough idea about how much current the EVSE can put out.
So in this case, that duty cycle relates to 10 amps, doesn't it, Ben?
Give or take, yeah.
Although we're plugged into a 13 amp socket, because we're going to be potentially charging for several hours, as a safety feature, the vehicle manufacturers limit that output to 10 amps. So that's what we'd normally get from a 3-pin plug.
So if we just want to talk about the second part of that waveform then, so we've gone from 9 to -12.
Yeah, so you can see that we get to a point here where we've got a step, and again, we don't have quite so much the step on the negative half of the waveform, and what's happening here is we're still getting the same output from the supply equipment, but the vehicle is then further altering that waveform to say that we're now ready to charge. So the vehicle has done whatever safety checks it needs to do, it's happy with the current, it's happy with the type of charging equipment, and it said, yep, everything's ready to go, please can you turn on the supply? So it signals that to the supply equipment by pulling this voltage down to about 6 volts. And as I say, because that's measured at the other end of the supply equipment as well, that will then turn on to relays within that unit, and we will then have mains voltage arriving at the car.
Yep, and at that point, obviously, then it goes through the onboard charger to get converted into DC, which then charges up your battery.
Now, this communication actually continues for the entire time that the vehicle is on charge. And there are some types of charging equipment that will actually vary the current that the vehicle is allowed to pull. So, for example, if you have a row of chargers, but the supply to that particular site isn't enough to charge every car flat out all the time, it can actually change the current that each car is pulling, so that perhaps when one is finished, it can then speed up the others because a bit more power has come available.
Yeah, exactly that. So, from a diagnosis point of view, the CP signal is really important because it helps give you an idea about what the communication from the EVSE is giving to the car. So it's all about, that PWM signal is all about the EVSE, not the car. So the car might not take as much as what the EVSE can deliver, but equally the EVSE can control the maximum amount of current available.
Absolutely. So, for example, if you've got a 30 amp supply, you've got a 30 amp cable, the car's only able to charge at 16 amps, for example, you'll actually find that the duty cycle will actually be saying 30 amps is okay, and the car will say, well, you know, I'll take 16 then because that's all I can take.
All right. So that's type 2 communication with a little bit more information. All right. Hope that helps. Okay, so the next test we're going to look at is 3-phase motors. So we're actually going to look at this from a current point of view, so completely non-intrusive. The biggest issue that we've got at the moment is that these 3 phases are getting more and more tricky to get hold of and actually get around the cables. So this e-Golf is a lovely demonstration as to what or how the actual 3-phase current actually appears on the screen. So it's a great useful training aid more than anything to get an understanding of how these motors are controlled. So there is a guided test for it. So if we go to the software, go electric vehicles, so you accept the warning, it's a system component test and it's 3-phase current. So again, we're going to load the guide and the settings in. So there's a bit of information about what we're actually looking for, as well as a reference waveform in the background. So we'll minimize the guided test. This is roughly what we're looking for. Now this is already built into the software, so if you just wanted to look at it from a visual point of view, software's free to download. You can have a look at all of these waveforms that are already on there. So, following the guided test, we need to connect our current clamps. So we have our 3 phases which are here. So we have U, V and W. All we're going to do is literally put the current clamp round each of those phases. Now again, this isn't possible on all vehicles. Some are easier than others, some are impossible. It's just a nice way of being able to see it though when you can. So if we move back to the software and actually start the scope, it's going to actually ask us for the probes to make sure that we've got them connected in the right place. So as you'll notice, as we connect each clamp, it should say detected. Whenever you connect these BNC Plus current clamps up, they actually automatically zero at the same time. So it just runs through a quick check, sets everything up for you, and zeroes it as well. Once that's all in, then actually it will automatically start the test. We have a trigger in place, so I'm going to run round, we're going to get the car up and running, and Pete's going to let me know when we've actually got something on the screen. Okay, so into drive.
Yeah, that looks great, Ben.
Yep, cool. Perfect, so this vehicle's not actually under load, so we don't get huge amounts of current being generated. Pete, if you just want to zoom in on like the second part of that waveform that we've got there. That's it. Perfect, and we'll go in again. Lovely, that's perfect, thank you. So as you can see, we've got our blue, red and green current clamps, and they indicate the different phases that we're connected around. Now, a three-phase motor has 3 phases. So with each phase, we have between, now again, this depends on how many poles it's also got, but let's just hypothetically say that between that one there and that one there is our 360 degrees, so 1 rotation. Then each of those phases are equally spread out. If you've got phases of varying different current heights as well, that could start to indicate that there's a problem with the winding itself. It's a bit hard to tell because we haven't got this on a static ground. So if you was actually out in a car park, actually putting the vehicle under a constant load at a constant speed, you'll get a better idea of the variation between each of those phases. So there's nothing different between this and what we normally do with PicoScope, where we're looking for those patterns, we're looking for those changes that are repeating. If, for example, one of these phases is considerably lower, then we know that we've already got a potential issue with one of the phases and how much current is being drawn from it. Okay, so just a bit of an insight into a 3-phase motor and the current that we can see using non-intrusive current clamps. Thank you.
Thanks to Ben and Pete there, really. I'm sure you found that really insightful, starting to look at working on electric vehicles with PicoScope. We're going to do a really overview. We're not going to do this live on vehicle, but really what we want to do is try and direct you now towards more content that's going to be appearing on our YouTube channel around testing with electric vehicles. And as we've already said on a number of occasions, we are assuming that if you are looking at videos and looking to start working on electric vehicles, that of course you have the relevant skills and training in your own market. If you're new to working with electric vehicles and you're unsure where to get appropriate training in your market, by all means contact us. We have distributors right across the world, and all of those distributors are able to point you towards you know, the appropriate training in your market. So please do contact us for that. So we're going to have a quick look at motor resolver signal, and I'm going to push you towards a case study that we've got on our YouTube site. So like all of the other tests that Ben and Pete have just shown you, we have our guided test, and the guided test is there exactly the same as we do for all of our internal combustion engine guided tests. It's there to help you make the connection and start to understand the waveform that you capture and what you expect to see. Because like any waveform, we don't expect everybody to understand it right at the beginning, and you're on a journey of learning through working with PicoScope. So there we've got on the screen an example of our motor resolver guided test and showing you how you would make the connection. And you are going to see a waveform for our motor resolver, something like this. So we would expect to see 2 signals that are amplitude modulated and 1 that is a continuous oscillation. So we've got that nice square blue to make it simple, that nice square waveform, and then we've got those amplitude modulated signals below. So that is normal. That is what we expect to see if everything is working correctly. Yeah, and then there's something that we can do here where we can do the X and Y position, which is something that's implemented in the PicoScope 7. I'm going to get Ben, he's going to talk you actually through a little animation on this after that. But again, as I said, what we really want you to do is take some time and go to our YouTube channel. It's PicoScope Automotive. Obviously like the videos on there, but most important, subscribe, because we are working on a lot more content working with electric vehicles. But this one here is one of our really excellent trainers over in Hungary, Mickey, who does a lot of work on electric vehicles. And this was a really nice case study in an issue with a motor resolver. So go over there and check that out. Really useful. It would just give you a really nice insight into how this component works, and more importantly, what to look out for when things start to go wrong. So we've got this short animation. Ben, are you okay to go?
Yeah, sure. Pete, do you mind pressing play for me? Okay, so as John said, motor resolvers. One thing to bear in mind there is that not all motors will use this same sort of motor resolver, so just be careful with the type. Make sure you verify the type of sensor you've got. So these are what you typically see on Priuses and Japanese stuff, so the VR sensor. The beauty of that is that it is completely it doesn't have any any touching parts, I should say, so it's contactless. We can only do this test with the 4425 and the 4425A. Any common ground scope is not possible to do with this test. We actually have to be floating across the actual coils that are output. So here we can see the resolver actually turning, and they are the signals, as John was saying, that you get out of the back. So the actual, oh, it's going to replay. That's exciting. We'll view it again. So again, we'll just talk about the bits that are in there. So we can see that the vehicle's moving. The resolver's connected to the actual rotor shaft itself. So the rotor speed and position is all dealt with off of this resolver circuit. So we have 3 separate coils that are actually built into that sensor. We have the one which is the fixed oscillation or fixed frequency signal, and then the 2 output signals. Again, only can do this test with the 4425A or 4425 floating input scope. So again, once it's up and running, we see that pattern change. All right. So the waveform that you'd expect to see from a motor resolver such as this particular type, you'll have these 3 output signals, as John was saying. So you have this fixed frequency signal. Now this can be anything up to about 10 kilohertz, and then you have the 2 outputs. So as the resolver actually turns, the amplitude is changed as it goes through this, fixed frequency signal. The clever thing that we can do, obviously, with maths, John briefly you did see it in the image. I don't know I can't remember if there's the animation that goes on the back of this, but you'll find that if you actually divide this signal from the frequency signal, you actually get the raw output of it. So you actually get this double sine wave image, which I'm not sure if it's... so yeah, here we go. So you can see it on this point here. Now, if you were to plot these two as an XY view, you actually end up being that they're 90 degrees apart. Because they're 90 degrees apart, as they rotate together, they actually make a perfect circle. So hopefully when XY is actually implemented into PicoScope 7, which should be hopefully this year, then actually we'll be able to plot that signal, even using maths, and actually see how that circle is generated. Perfect. Okay, over to you, John.
Thanks, Ben. Excellent. Yeah, so we only wanted to cover that briefly, but we're really just trying to point you towards, obviously, more content as we create it there up on YouTube. So just a recap on where we are with our guided tests within PicoScope 7. So you've got that electrical vehicle testing there. So we've got 15 tests at the moment within the software. And as Ben showed you earlier, a lot of those also have really nice videos, so we can show you, just like we have today, testing live on a vehicle so you can see all the connections, you can see the waveforms, and most important, you can see Ben and our other colleagues understanding what the waveform is showing us. Okay, so we're now coming on to our case studies. So what we want to do is just give you some examples of where PicoScope fits into problems and issues you're going to start to see with electric vehicles coming into your workshops. So I'm going to pass you over to Ben, and he's going to take you through a really, really nice case study working on an issue with an Audi Q7. Over to you, Ben.
Okay, thanks, John. So Steve did a wonderful case study on an Audi Q7e. So it was all about focusing on that the vehicle is a plug-in hybrid, and the problem is that it wouldn't charge. So you connect it to a charger, nothing would happen. So fortunately for this particular vehicle, it would actually still recharge the battery through the engine. But we'll talk through the case study and what we found, and hopefully it will help. I mean, charging issues are predominantly a relatively big issue, or one of the more common complaints. One of the more common issues,
yeah.
So we'll talk through it. So yeah, a bit of an understanding first. The vehicle was failing to charge from the mains. With this particular vehicle, obviously mode 2 is basically what we showed earlier. But this would also have an issue with charging on the slightly higher one, so the DC charging as well. So it generally just wouldn't communicate. It wouldn't actually do this. So when connecting it to a car, both the charger and the vehicle recognise the charger is connected. So that's one step of the hurdle. It's right, is there something connected? Yep, the car inside actually on the screen, it actually shows you a little cable connected to the charging port. And actually the proper Audi e-tron EVSE actually tells you that it's plugged. So it's recognising that that proximity circuit is completing. One thing that was noticed was that when we actually connected the charger to the car, if you notice, you should be able to listen to it, hopefully. This was filmed in a workshop, hence the spanners flying around. You can just about make it out. So basically the lock ping is oscillating between being engaged and not engaged. And then a red warning light flashes up on the actual charging port to indicate something's failed, something's gone wrong. Prior to us actually getting involved with this vehicle, the car was actually had the charge inlet socket, which actually has the locking solenoid fitted to it as well. That was replaced. Didn't fix it. First one to check then is actually to look at that CP signal then and see what's coming in. So we know that using the EV guided test, we actually have a known good. We can see that step change, as we mentioned earlier. The top one is actually the reference waveform from the guided test, which are easily to create within the PicoScope 7 software. And in the darker blue colour, that's actually the live signal that we took off the vehicle. So you can quite clearly see that we get that 9-volt drop, so indicating that the charger has been connected. The car's set that voltage level, but we get down to a -12, so then the EVSE is now outputting that oscillating -12, +12, but we obviously get that drop to 9. But then it doesn't actually do this next part. So this change to 6 volts then indicates that the car is ready to accept a charge. We don't get that happen. So understanding how things work and how things actually, this charging section all sort of works together with the car is going to help us understand where the fault lies. So we can see here, when we actually connect the car, we get that 12 volts, as Pete mentioned earlier. We don't often see that because actually it's so quick that actually it's already dropped down to 9 volts by the time it's actually connected. We then get it changed to this ±12 volt AC signal. And then this resistor at this point is actually switched, which actually changes the drop. And then charging can take place. We know that this point here is not happening. The car is not happy about something. It's not changing its state. So knowing that CP is not changing state, we can then move to PP. So if proximity isn't correct, then we know that the charging is not going to take place. We do already know, though, that the car is detecting that something's plugged in. So just again, verifying that something is changing is enough to get you going. Again, having a known good would have been good to see, but we're almost fairly comfortable with that. But again, the evidence is there to back it up. Now, there's no warnings in this car, nothing to indicate that there's a fault. We did a scan. we found that there is a charging plug lock mechanical malfunction, which probably explains why the charging inlet socket was replaced in the first instance. Scan tools, they're great, they work in partnership with Pico. However, this is a great one which indicates as to why there sometimes it can lead you astray. We have a current here of 15.7 amps, which on the charge lock socket or lock pin, if 15.7 amps was to flow through those cables, it would melt and catch fire. We expect it's a scaling issue. It's probably more like 1.5. Wiring diagrams, obviously important. We need to get all this information together to actually now start to break down what's going on. Now, here we actually have this lock pin. So earlier in the video, you actually heard the lock pin actually changing its state. So we're flicking between locked, engaged, not engaged. And it's also reflected in the current because we've got both positive and negative. Interestingly, at this point, if you were to look closely and put some rulers in around this little spike, it's closer to the 1.5 amp mark. So, we know that the current is not exceeded, as suggested by VCDS. Position voltage for lock pin engaged around 6 volts, so we actually have the position sensor up on this top line, so we're showing how that lock pin is detecting its change in position. And the position voltage for lock pin disengaged is around 3 volts. Okay, so they're key bits of information together. So what would you do next after that point? Well, we need to get a known good. We need to get a bit of back-to-back testing. Fortunately, we have our lovely e-Golf here. So we were able to actually use this. It has a very similar onboard charger to this Q7. Interestingly, at this point, we know that this lock pin voltage position for the Q7 was 3 volts for unlocked, 6 volts for locked. For the e-Golf, it was 3 volts for unlocked, roughly, and then 9 volts for locked. So we've got something that's different there. At this point, the customer's getting a little bit frustrated and just the old part swap comes into place. They actually got hold of a second-hand onboard charger. And, surprise, surprise, fitting the second-hand onboard charger and following coding, EVC was connected and charging commenced. So we've actually changed this. Now, we know that the pin position voltage has now changed, and by putting a reference in, you can actually see the difference between the two. Now, me and Pete were having a bit of a discussion about this, weren't we, about what's actually gone on. So our understanding is we've got potentially a 12-volt input signal to that lock pin position sensor. Yeah?
Yep, so that comes from within the onboard charger.
Yep.
It's sent down that wire to that position sensor, and then the position sensor will pull that voltage down depending on the position.
Yeah, absolutely. So what we think's actually happened is that there's an issue with inside that onboard charger on this circuit. Now maybe it's high resistance, maybe a bit of boards damaged somewhere, maybe there's a bit of water ingress. For whatever reason, our onboard charger, original onboard charger, was not allowing that 9-volt signal to get back to, well, being sensed by the onboard charger. So therefore, it didn't know its lock pin position. Fitting the new one, we've got the evidence to back it up. We have verification of the fix. So finally, one last thing you could do is actually you could hook the diff probe up, actually check the CP circuit and actually see the change in state. So again, it adds that verification to your now fix. So if you look here, we've actually got this change of state. We can see we're up at about 9 volts. We drop down to 6, the car is now charging. And then we've actually forced the stop by hitting the button or hitting the unlock button on the key fob. That now stops charging. And we can see actually here, by using a current clamp, we can actually see the change in the lock pin motor to actually force its change in position.
So what we're seeing here, Ben, this is something that's specific to the Type 2 charging standard, because on the Type 1, we've got a release button on the cable. Now that actually changes the electrical signals of the car, so it knows that someone's about to pull the connector out. On the Type 2, we don't have that. So every car that's got Type 2 will lock the connector in before it starts to charge. And of course, it needs to see that lock pin in the correct position before it will then start the next part of the process and turning on the supply. So what it looks like we're seeing in this case is the onboard charger isn't sending the right voltage down to the position sensor. That's causing a low voltage on that line, which it's then interpreting as the lock pin not being in the correct position. It's having another go by firing the lock pin again and again, and eventually giving up.
Absolutely. So it just goes to show that there's still a lot to do with fixing these cars, and there's still an awful lot of things that can go wrong. So understanding knowing what the signal should look like is always just as important as it ever was before. All right, over to you then, John.
Thanks, Ben. Really, really nice little case study there, and hopefully you can start to understand how we apply PicoScope to some issues. So, just want to take a moment, actually, particularly for thanking Pete to come along and be a part of this video today, and hopefully we can coax him back to do more videos with us in the future. But I'm just like to talk to you a little bit about Pete's company, Hevra, and what they do. Obviously based in UK and real specialists around support and helping workshops and technicians with issues that you're going to start to see with electric vehicles. So it's available in terms of a tech support line for the UK market, but he has opened up the data that they're creating and producing every day for worldwide technicians. So please go on to his website. That's fixev.org there, and have a look, and you can subscribe to everything that they do. So this is just a really, and this is something that we think is really, really valuable. These really, really great spec sheets to build up your understanding of technology on specific vehicles. And also in there, if you're lucky enough to be in the UK, he's getting a really nice map together of where good and trusted electric vehicle workshops are right across the UK. So really, Pete, thanks very much for coming along and doing this today.
Yeah, no, thanks.
I don't know whether you want to add anything to that.
Yeah, basically these are the guides that we publish because we realised quite early on that some electric and hybrid vehicles were very different to others. So different brands were using very different technology in terms of everything from battery chemistry to thermal management. So we do these guides for each vehicle. These are all available to our members just to let people know the difference. And all of our members benefit from our technical support as well. If it's something that we've seen before, then obviously we can guide you through it to find the problem. If it's something that we haven't seen before, then we'll work with you to get to the bottom of it. We'll put everything we can in to get into the bottom of that problem because, of course, it gets the car fixed for you and then we know for next time. So that's what it's all about.
Yeah, no, I have to totally agree. I mean, Pete and Hevra have helped me and Steve out on a number of cases. That Q7 was one of them, actually, and a couple of the other ones that you see on our website. So it's a really great service that they're providing. And like I said about the guides and the vehicle spec sheets, if you like, if you don't know how it works, you can't fix it very well. So they're a great first point of call in the sense of knowing where all the different bits are and how they actually interact. So first rate, proper job.
Thanks, Ben. Okay, so we wanted to move on to a bit of MVH, noise, vibration and harshness. And the reason this was, we found this particularly interesting with electric vehicles is because if you get a noise that's related to the speed of the vehicle, this is very different to dealing with it in a conventional vehicle, because in a traditional car, you'll have the engine, you'll have a multi-speed gearbox, whether that's manual or automatic, and that means it's very easy to change the relationship between engine speed, vehicle speed, and all the different gears in order to find a potential cause of a noise. So, for example, if you've got a noise that's there when the engine's running but the vehicle's not moving, then it's obviously not going to be a wheel bearing.
Absolutely, yeah. And it's important to point out for EVs as well is that there's less rotating components. So actually, you know, you're kind of already in the right area, but because they're quieter as well, you haven't got the noise of the engine, the drivers are automatically more susceptible. You're going to notice noises more than you would have done. And the real challenge is because everything turns together. So when the vehicle starts moving, the motor, every part of the gearbox, the drive shafts, the wheel bearings, the wheels, the tyres, everything all turns together. You've got no gear ratios that you can alter any of it. So we need to have better methods of pinpointing where a noise comes from. And we've got an example of a noise here. Cool. So as we said, this vehicle is obviously, you can hear the noise, and something Pete actually sort of you know, you heard yourself as well. It was quite an obvious one. As we said, drivers are more aware of noise now because EVs are inherently more quiet. A couple of things to point out from that. You can clearly hear that the noise level increases, or the noise increases in the frequency as the vehicle speed increases. And the best bit about MVH is, you know, we said, it's so easy to hook up. It's completely non-intrusive. You're not doing anything unsafe. You're not like you're pulling the top of the inverter off and trying to measure voltages and things like that. It's all non-intrusive work. So.
Yep, so I attach this sensor. There's a nice magnetic mount that comes in the MVH kit, isn't there? And there's a nice steel bolt here that you can put it to on top of the gearbox mount. So attach that onto there, put a microphone under the bonnet as well, just literally just tied that to the coolant bottle, and so it was listening within that area. And then of course you can record this waveform so that you can see exactly what that sound looks like, for want of a better term.
Definitely. So from here, obviously MVH is, there's no getting around it. It's a tough subject. Hopefully with just visually seeing how things change gives you an idea of what's going on though. So straight away you can see from that picture there is a huge amount of energy, let's call it that, around the sort of 600 hertz mark, and that was being picked up by the accelerometer. But by looking at the different views, so remember that within MVH, it's not just the FFT we're interested in, so you also have 3D frequency view, there's the time domain, and there's obviously bar graphs as well. So if we look at the different types of patterns that you can get, the time domain was the best one to view this in. You can see here that it's got a definite shock, which actually in all three axes, so you have X, Y, and Z, in this instance, it's actually in the Z axis that is the most, or is being felt the most amount of energy is being transferred in the Z direction. So with some better understanding of gearbox arrangement, you could actually pinpoint this a bit closer. With multiple sidebands, I mean, if we look at that original one, when we talk about sidebands, you have your inherent fundamental frequency of interest, and then you have areas around the outside of it. Typically, from our experience, they are, that would point towards a bearing-related issue. Cool.
Yeah, and luckily on this particular vehicle, because the original Zoe, the earlier version, the motor and the gearbox actually came as one assembly. But this being the later version, the 5AQ motor code, you can actually get the gearbox separately. And we do find, not just for mechanical things, but for the electronic parts as well, that Renault are quite good at selling individual parts of the system separately, which is great for keeping the cost low for the customer. It makes a more profitable job for the garage as well, because there's normally more labour and less on parts. But what it does mean actually is means you need to be better at pinpointing the problem, because if something comes as a whole assembly, it's easy just to replace that whole thing, whereas when things can be broken down into smaller parts, it's better for the customer, it's better for the garage, but you do need to make sure you're replacing the right part.
Absolutely. It's also better for the environment. I mean, you don't want to throw away these huge components when actually it's just a couple of little bits that actually need to be replaced. So
absolutely.
Better diagnosis, better ways of testing. It's always got to be a plus for everybody.
Yep.
So gearbox was replaced, and again, benefits with Pico, it's all about getting that pre and post capture, the verification fix. The gearbox part was replaced. The captures were taken again. With MVH, it's all sort of relative to a degree, so trying to make sure that you do the same test and you're putting the things in the same place as before will make sure that your verification is an equal match to how it was before. Immediately, I mean, if we play the sound, you can clearly hear that shock that we had before has totally gone. And you can also see it visually in the FFT as well. So if we just have a little look back through here. So this is what I was saying earlier about the different views. So this would be the 3D frequency view, so you can sort of see where it changes over time, over a bigger expanse of time captured, so viewing. And then obviously back in the time domain, you can clearly see that those shocks are no longer there. Again, the beauty of it, you can actually add references in MVH, a bit like you can do with normal PicoScope software. So here we have the before and after all on the same screen. It's a very easy one to give to the customer and go, we have changed something and it's now clearly different. I mean, the sound alone is enough, but using this actually gives you more evidence, backs it up even further. There we go. So yeah, as mentioned, MVH-related issues are going to be more obvious to drivers in EVs. Being able to compare before and after is so important, and especially when it becomes something that the customer can see that something's been fixed. Sometimes it's not so obvious that you've been in there and had everything about and spent 2 days working on something. But if you've got a bit of paper that shows you what you've done and what's changed, adds complete value to what you're doing.
And it's nice for it to be a bit more scientific as well, because you know, when you're in that workshop environment and you've replaced a part and you're road testing the car, you're sometimes a bit paranoid whether you fixed it or not, and to actually have a scientific way of measuring it, you can say, oh well, actually it's quite clear that
absolutely something that whatever we've done has changed something. As I mentioned earlier, obviously replacing parts, something we don't really want to do. You don't want to replace big lots of parts for lots of money when you can actually replace smaller components. That obviously has massive benefits to both, as Pete said, the garage, the customer, ultimately the planet as well. So I think that kindly segues into John and Pico Planet.
Thanks, Ben. Very nice little link there. Professional as always. Okay, so again, thanks to the guys there for taking us through those 2 little case studies. Excellent, and particularly showing just how important MVH is starting to become when working on electric and hybrid vehicles. So finally, let's have a quick look at this. So look, we know everything's got to change, and the way we think about transport and the way that we view the automotive industry is changing. Our move towards an electric vehicle is part of that. But also, when we start to look at this is a autonomous vehicle that will be able to drive itself around. Autonomous vehicles are great because what we actually want, the embedded emissions in our vehicles, is huge. So using cars, and more importantly HGV and vans, we think about them moving around in the future. The fact we're using those all the time rather than sitting still. If we think about the average motor vehicle, it actually sits still for 97% of its life. It sits on our driveways, and that's a massively inefficient use of carbon when we consider, you know, that a modern car has somewhere between 10 and, for a larger vehicle, 20 tons of embedded carbon. So we have to start to think about how we use it. And technology, of course, is our friend, and there's huge amount of work going on with things like I'll show you there. So it's just an example. We're hopeful for the future, we're looking forward to a future, and we're embracing the change, and our move towards helping you guys start to understand and work with electrical vehicles is, of course, all a big part of that. Brilliant. Well, look, just to finish up, thanks again. Huge thanks for Pete for coming along and being part of the video. You know, his insight and his understanding in working on electric vehicles every day is huge, and like I said earlier, hopefully we can coax him along to do more. And as always, thanks to Ben for helping put all of the presentations together and making it all work. So thanks for joining us. We do plan lots more sessions in the future, but for now, goodbye.